Based on the ideas so far we have discussed, we shall solve some of the problems related to those ideas. First problem, in an electrolyte 3.2 to 10 power 18 bivalent positive ions drift to the right per second, while 3.6 in 10 power 18 monovalent negative ions drift to the left per second. Then the current is. We have to calculate the magnitude of current as well as the direction of flow of current here, right? So it is given this many number of bivalent positive ions. Bivalent positive ions in the sense I can take it as 2e plus even. They are drifting towards the right. And monovalent electron, E minus, is drifting towards left. Movement of charges are taking place in a given electrolyte. As you know very well, in the conductor, the current flow is mainly due to the flow of electrons. In an electrolyte or in a liquid, current flow is due to positive and negative ions. In a semiconductor, as you know, current flow is due to electrons and holes. In gases, current flow is due to positive ions and negatively charged electrons. What is the difference between negative ion and negative electron? A single negatively charged particle is negatively charged electron. If a neutral atom catches an electron, then it will become a negative ion. So the mass of negative ion and negatively charged electron will not be the same. Electrons and negative ions are not the same. Negative ions are entirely different. If a neutral body loses one electron, then it acquires positive charge. If a neutral body gains one electron, neutral atom gains one electron, then it will become negative charge. It will become negative ion. An electron is a negatively charged particle. Here we are speaking about the movement of charges in liquid, right? So current flow must be calculated. I can say current I equals Q by T, which is Ne divided by T. The total current I is due to the sum of current due to positive charges and current due to negative charges. So I can write here N plus E plus divided by T plus N minus E minus divided by T, and this moment is for per second, so time is 1 second. Number of positive charges or positively charged ions is 3.2 into 10 power 18. Number of negatively charged ions is 3.6 into 10 power 18. Charge of positive ion and the charge of negative ion are one and the same, 1.6 into 10 power minus 19. Whether it is monovalent or bivalent, that is important. Substituting this data, we can calculate the amount of current. N plus is 3.2 into 10 power 18 into, since the positive ion is bivalent, we can write 2 into 1.6 into 10 power minus 19 plus current due to negatively charged electron is 3.6 into 10 power 18 into 1.6 into 10 power minus 19, right? So 3.2 plus 18 minus 19 minus 1 plus 18 minus 19 minus 1. So 2 into 1.6 is 3.2. 3.2 into 3.2 into 10 power minus 1 plus 3.6 into 1.6 into 10 power minus 1. On simplification, you will get 1.6 ampere as the positive value. So if the current is positive, then we can say here the current flow takes place along the direction of the positive ion. What is the direction in which the positive ion is moving? It drifts towards the right. So it moves towards right. I equals plus of 1.6 ampere, which moves towards right. Then question number 2. The dimensions of a block are 1 centimeter, 1 centimeter, 100 centimeter. How will you read this? 1 centimeter by 1 centimeter by 100 centimeter, LBH. Its specific resistance of its material is 3 into 10 power minus 7 ohm meter. Then the resistance between the opposite rectangular faces is resistance between opposite rectangular faces. So we have to draw the diagram here. They have given 1 centimeter, 1 centimeter, and then 100 centimeter. This is the rectangular face. So you are asked to calculate the resistance between the rectangular faces. This is the rectangular face. So R is equal to rho into length of the block divided by area of rectangular face. We saw this formula earlier. Value of electrical resistivity rho is given as 3 into 10 power minus 7 ohm meter. Length L is this one centimeter. So 1 into 10 power minus 2 meter. Then area is B into H, which is 1 into 10 power minus 2 into 100 into 10 power minus 2. So this goes off. This is 1 into 10 power minus 2 itself. So resistance R equals 3 into 10 power minus 7 into 1 into 10 power minus 2 divided by 1 into 10 power minus 2. So 3 into 10 power minus 7 ohm. This is the resistance across the rectangular faces. Resistance across the rectangular faces. You can also calculate the resistance across the square faces between these two faces. Here, the length between the two square faces will be 100 centimeter, and the area of the square faces is 1 centimeter. So we can calculate resistance between square faces also. R square is equal to 3 into 10 power minus 7 into length is 100 centimeter. So 1 into 10 power 1 divided by area of this square face is 1 in 10 power minus 2 into 1 in 10 power minus 2. So 1 in 10 power minus 2 into 1 into 10 power minus 2. So we will have 10 power minus 4 goes off, 10 power minus 3. So this is 3 into 10 power minus 3 ohm. See the difference. For rectangular faces, the thickness is less, so the resistance is less. For square faces, the length is more, so resistance is more, 3 into 10 power minus 3 ohm. In an electrical cable, there is a single wire of radius 9 millimeter of copper. Its resistance is 5 ohm. The cable is replaced by 6 different insulated copper wires. The radius of each wire is 3 millimeter. Now the total resistance of the cable is. So we can show it with a diagram. A cable whose radius is 9 millimeter is replaced by another cable which is made of 6 wires. Which is made of 6 wires. 1, 2, 3, 4, 5, 6 wires. So, like this. Made of 6 wires. Each single wire has a radius which is given by 3 millimeter. 3 millimeter. So what we can say is, or what we can understand is, the length of the cables are same. Length of the cables are same. This one is replaced by this one. So these two resistances, effective resistances are equal. They are asking, means the resistance of this particular cable is 5 ohm. They are asking you to calculate the resistance of this cable having 6 such cables. Resistance initially for a single cable is rho L divided by E. Rho L divided by A. Actually, they have given the data in terms of radius, so I can take it as rho L divided by pi r squared. Pi r squared. This is 9 millimeter. So rho into L. Length is unknown, divided by pi into radius is 9 into 10 power minus 3 the whole square. Resistance of a single wire is also rho L divided by A, rho L divided by pi r square, rho L divided by pi into 3 into 10 power minus 3 the whole square. 6 such wires are joined parallel to form the cable. What kind of combination is this? Parallel combination. So, the equivalent resistances, as the resistances are, the cables or wires are all identical, I can say R equivalent equals R by 6. R equivalent equals R by 6. So 1 by 6 times it of the resistance of the single wire. So 1 by 6 into rho L divided by pi into 3 into 10 power minus 3 the whole square. From this expression, I can calculate rho L divided by pi as R into 9 into 10 power minus 3 the whole square. R into 9 into 10 power minus 3 the whole square. R is given 5. R is given 5. So I can write 5 into 9 into 10 power minus 3 the whole square. So instead of rho L by pi, I can substitute 5 into 9 into 10 power minus 3 the whole square. So R equivalent is 1 by 6 into rho L is 5 into 9 into 10 power minus 3 the whole square divided by 3 into 10 power minus 3 the whole square. This power goes off. I can write 1 by 6 into 5 into 81 divided by 9. This is 9. 45 by 6, 7.5 ohm. So the effective resistance here is 7.5 ohm. For the earlier one, it is 3 into 10 power minus of 7 ohm, and for the first one, it is 1.6 ampere to the right. Question number 4. Two wires A and B of same material and the same mass have radius 2r and r. If resistance of the wire A is 34 ohm, what is the resistance of the wire B? Right? They are of same material. If material are same, then resistivity is same for both the wires, or they are made of same material. Mass is also same. If mass is same, I can say volume is same, because density equals mass by volume. Volume of a given density is constant, mass is also same, so volume must be same. Volume must be same. Volume is area into length, so A into L must be equal to a constant. A and L are inversely proportional, so I can take L is inversely proportional to A. L is inversely proportional to A. Two resistances are compared, RA and RB. I can write same material, so resistivity is same. L1 divided by LA divided by A suffix A divided by rho LB divided by A suffix B. They are of same material, they got cancelled out. And this is equal to LA divided by LB into AB divided by AA. L and A are inversely proportional. So, I can write LA as LA is inversely proportional to AA. So, I can write AB divided by AA into AB divided by AA. Actually, instead of LA by LB, I have taken the reciprocal of AB and AA. So, this is equal to AB square divided by AA square. Area is pi r square, so pi r b square the whole square divided by pi r a square the whole square. Pi got cancels out, so rb power 4 divided by ra power 4. Radius of b is r, radius of a is 2r, the whole power 4. This is ra divided by rb. This is 16. RB equals 16 into RA. RA is given 34 ohm. So 16 into 34, 544 ohm. This is right. Masses of three wires of same metal are in the ratio 1:2:3 and their lengths are in the ratio 3:2:1. Then the electrical resistances are in the ratio. Electrical resistances are in the ratio. Masses of three wires of same metal. Same metal here refers to the resistivity, rho. Rho. So rho is same for both the or all the three metals. But their length ratio and mass ratio are different. Mass ratio is 1:3 and length ratio is 3:2:1. Number 5. The ratio of masses M1:2, M2:2, M3 is equal to 1:2:3. Ratio of the lengths L1:L2:L3 equals 3:2:1. Then they are asking you to calculate the ratio of resistances R1:2, R2:2, R3. R1:2, R2:2, R3 can be calculated easily. Before going to do that, when you write the expression for resistance, this has to be calculated. When you write the expression for resistance, R equals ml divided by NAE square tau, where m by NE square tau is rho. This is rho L divided by A. This is how you write the expression. This m is mass of the electron. Mass of electron. So you cannot substitute like this. Right? You have to bring out the value of mass of the wire, metal wire. So multiply and divide by L in this expression. So R equals rho L square divided by A into L, which is nothing but volume. As density equals mass by volume. As density equals mass by volume. Volume equals mass divided by density. So mass divided by density, density will go up. So R is equal to density. Same metal, in the sense density is same, electrical resistivity is same. So R proportional to L square divided by capital M. Now, if you write the ratio R1:2, R2:2, R3 is equal to L1 square is to L2 square is to L3 square divided by M1 is to, I can write L1 square by M1, L2 square divided by M2, L3 square divided by M3. The length ratio are 3:2:1. So 3 square is 2, 2 square is 2, 1 square divided by mass ratio 1:2:3. So 9:2, 2 square 4 divided by 2 is 2, 1 square is 1, 1 divided by 3. And cancelling this, you will have 27:2, 6:1. This is the ratio of resistances. 27:2, 6:1. So D option. Of a hollow tube is 5 meter. Its outer diameter is 10 centimeter. Thickness of its wall is 5 millimeter. If resistivity of the material of this tube is 1.7 × 10⁸ ohm meter, then the resistance of the tube will be. We already saw the resistance of different shapes of the conductors. This is a hollow tube given. This is the hollow tube given, and they have given the data. The length of the hollow tube is 5 meter. L equals 5 meter. Its outer diameter is 10 centimeter. Diameter is 10 centimeter. So radius will be 5 centimeter. Thickness is 5 millimeter. So inner radius will be 4.5 centimeter. 5 millimeter is 0.5 centimeter. So inner radius is 4.5 centimeter. So A equals 4.5, B equals 5 centimeter. Electrical resistivity rho equals 1.7 into 10⁻⁻8 ohm meter. Then the resistance of the tube is, as we saw the expression for the hollow tube, R equals rho L divided by pi into B square minus of a square. We can write 1.7 into 10 power minus 8, length is 5 meter, divided by pi is 3.14 into b square is 5 square. Actually it is in centimeters, so finally you will be getting into, you can bring out outside the bracket, minus of 4.5 the whole square into 10 power minus 4. This is 10 power minus 4, 5, 8.5 divided by 3.14 into 25 minus of 4.5 into 4.25, 20.25 into 10 power minus 4. On simplifying this value, we will get 5.6 into 10 power minus 5 ohm. This is the resistance of this. Two resistances R1 and R2 are made of different materials. The temperature coefficient of the material R1 is alpha and R2 is minus beta. The resistance of the series combination of R1 and R2 will not change the temperature if R1 by R2 equals. The resistance of a series combination of R1 plus R2 means you have to sum up the two resistances. If they don't change the resistance value, if they don't change the temperature value, then when it will happen? At what ratio there will be no change in the temperature? R1 by R2. What is the ratio of R1 by R2? This is the question. As we saw, the temperature dependence of resistance as RT equals R0 into 1 plus alpha T. Here we can take the series combination of resistances will not change the temperature. I can write R1 equals R1 into 1 plus alpha T, and R2 is equal to R2 into 1 minus of beta T. R2 into 1 minus of beta T. Because for the first metal, temperature coefficient of resistance is alpha. For the second metal, it is minus beta. When we combine this in series, R1 plus R2, this will be equal to R1 into 1 plus alpha T plus R2 into 1 minus of beta T. So temperature is not changing. R1 plus R2 equals R1 plus alpha R1T plus R2 minus of beta R2T. R1 plus R2 can be taken out this side. Minus R1 minus R2. This is equal to alpha R1T minus of beta R2T. So alpha R1T equals beta R2T. This gets cancelled out. R1 by R2 is equal to beta divided by alpha. If R1 by R2 ratio is equal to beta divided by alpha, then the resistance of the series combination of R1 and R2 will not change the temperature. This one. And then question number 8. The lowest resistance which can be obtained by connecting 10 resistances each of 1 by 10 ohm. As we saw a statement, the effective resistance will be less than the least value only when the resistors are connected in parallel. If 10 resistors are connected in parallel, then the effective value will be less than the least. You will be getting lowest value of resistance. As 10 resistances are connected, all the resistances have 1 by 10 ohm. We can say they are all identical. So the parallel combination effective resistance is Rb equals R divided by N. The resistance of R is 1 by 10 and there are 10 resistors. There are 10 resistors. N equals 10. N equals 10, R equals 1 by 10 ohm. So when these resistors are connected in parallel, then only you will be getting the lowest value of resistance. So you will have 1 divided by 100 ohm. So the lowest value of resistance is 1 divided by 100 ohm. And for the earlier question, it is beta divided by alpha. Resistances are joined in parallel, whose resultant is 6 by 8 ohm. Two resistances are joined in parallel, whose resultant is 6 divided by 8 ohm. One of the resistance wire is broken. and the effective resistance becomes 2 ohm, which means this resistance alone will remain, its value is 2 ohm. If one of the resistance is broken, the effective resistance becomes 2 ohm. What does that mean? If this resistance does not exist, the effective resistance is 2 ohm, which means this resistance has a value 2 ohm. Now what is the resistance of the broken wire? What is the resistance of this wire? So I can write 1 by Rp equals 1 by R1 plus 1 by R2. I consider R2 is broken. R1 has got the value 2 ohm. So 1 by 6 by 8 equals 1 by 2 plus 1 divided by R2. So 8 by 6 minus 1 by 2 equals 1 by R2. So 16 minus R6 divided by 12 equals 1 by R2. 10 divided by 12 is 1 by R2. R2 equals 12 divided by 10. 6 divided by 5 ohm. R2 is 6 by 5 ohm. This is the resistance value. The total resistance between ABs. Actually, the resistances are connected like this. This is AB, 2 ohm, A2, 2 ohm. This is 1 ohm, 1 ohm, 1 ohm, 1 ohm. A2, 1 ohm. As I told you earlier, these two resistances are redundant, which means no current will flow through these resistances because they are open. So I can remove these two resistances from the circuit. Simple. Now, these two resistance, this one resistance, this is 4 ohm, and these two resistances. These are all in series. So 4 plus 2, 6 plus 2, 8. So all these resistances get simplified as 8 ohm. 8 ohm and 8 ohm. So in the first case, I can write 1 by Rs equals 1 plus 1 plus 4 plus 1 plus 1. So it is 8 ohm. This 8 ohm and 8 ohm are in parallel. So 8 into 8 divided by 8 plus 8, 64 divided by 16, 4 ohm. So these two resistance goes off and it will become 4 ohm. Once again, this 4 ohm and this 4 ohm get added up and will become 8 ohm. Eight ohm and 8 ohm are in parallel, so it becomes 4 ohm. 2 ohm, 4 ohm and 2 ohm are in series across AB. So this is once again 8 ohm, which is 2 plus 4 plus 2, 8 ohm. So effective resistance is 8 ohm. The option. As a continuity, we shall go on to the question number 11. Find the equivalent resistance of the circuit between the points A and B as shown in the figure. Each branch is of 1 ohm. Each and every branch has a resistance 1 ohm. Like this, you can mark all the resistance values as 1 ohm. They are asking you to calculate the equivalent resistance across A and B. We shall see question number 11. Actually, the circuit has a symmetry. If you look at the case, this is A, this one is B, and then this is how the circuit has been given. All the resistances are of 1 ohm each. We can take a perpendicular bisector for this reference line AB, so that we can say these points are at the same potential. Now the circuit can be reconstructed like this. I am taking these two resistances to this particular point. I am connecting the common potential points here, so I can show it. I am taking this resistances, two resistances to this common potential point. Similarly, these two resistances can be taken to the other common potential point at this point. I am reconstructing the circuit now. These are the points across which the effective resistance has to be calculated. Now, there is a symmetry about this reference line AB. This circuit arrangement and this circuit arrangement both are similar, they are symmetrical. So, if I solve the effective resistance for this particular arrangement, then I can apply that for this arrangement also, and then finally I can find out what is the effective value of resistance across AB. Here, we can say this resistance is 1 ohm, this one is 1 ohm, this is 1, this is 1, this is 1, this one is 1, this one is 1 ohm, this resistance is 1 ohm. If you look at this particular case, I am taking the circuit. I am taking this circuit along. I have joined already these two resistances. If you look at the case, these two are in series, so effective resistance can be taken as 2 ohm here. These two are in series, so 1 ohm and 1 ohm in series will become 2 ohm. This one is 1 ohm, 1 ohm, 1 ohm, 1 ohm. This 1 ohm and 1 ohm are in parallel because this is common potential point. This 1 ohm and 1 ohm are in parallel. So for parallel resistances, we can say Rp equals, or 1 by Rp equals 1 by 1 plus 1 by 1. So it is 2. 1 by Rp equals 2, Rp equals 1 by 2. So this resistance is taken as 1 by 2 ohm. And this resistance is also replaced by 1 by 2 ohm. 1 by 2, this is 1 ohm. So we can minimize this circuit by reconstructing it once again. This half ohm and half ohm will become 1 ohm, and this 1 ohm is there, this 2 will become parallel, this 2 become parallel, and this 2 become parallel. We can finish it off. So half and half 1 ohm. 1 ohm and 1 ohm are in parallel, so we will have Rp equals 1 by 2. So the effective value of this resistance will be 1 by 2, and these two resistances are in parallel. So we can write here 1 by Rp equals 1 by 2 plus 1 by 1. It is 3 by 2, so Rp equals 2 by 3. So this resistance or this resistance has a value 2 by 3. So I can reconstruct this one as 2 by 3 ohm, 1 by 2 ohm, and then 2 by 3 ohm. So we can say here 2 by 3 ohm, 1 by 2 ohm, and 2 by 3 ohm. These three resistors are in series now. So for this equivalence, we can take Rs equals 2 by 3 plus 1 by 2 plus 2 by 3. So 6, 4 plus 3 plus 4. So Rs is equal to 11 divided by 6. So this resistance has a value 11 divided by 6. Now, if upper half has 11 by 6, lower half has the symmetry. So lower half will also have 11 by 6 ohm. So I can minimize the circuit as This is 11 by 6 ohm and this one is 11 by 6 ohm, and these two 1 ohm resistances are in series and their effective value is 2 ohm. 2 ohm. So between A and B, we have 11 by 6 ohm, 2 ohm, 11 by 6 ohm which are in parallel. So as a final step, 1 by Rp equals 1 by 11 by 6 plus 1 by 2 plus 1 by 11 by 6. So you can write 1 by Rp equals 6 divided by 11 plus 1 by 2 plus 6 divided by 11. If you take LCM as 22, then 12 plus 11 plus 12. So this is 35 divided by 22, which is 1 by Rp. So Rp equals 22 divided by 35 ohm. 22 divided by 35 ohm. So for the first question, option is C, 22 divided by 35 ohm. So what exactly we are doing is, we are first dividing the, or we are taking the perpendicular bisector for this particular diagram, for AB. In a perpendicular bisector, as the circuit diagram is symmetrical, all the resistances are 1 ohm, all the points which are lying on the perpendicular bisector will be on the same potential. Since there is no resistance to be removed, we are connecting the common potential points or same potential point as a common point. So I am shifting this one, this resistance over here. I am flipping this resistance over here and this resistance over here. Then this two will become parallel, this two will become parallel. And then I am just leaving the lower half because there is a symmetry. I am solving the upper half of the circuit alone, and from which we can take the value for lower half circuit also. So these two are in parallel, these two are in parallel, their effective has been formed, and that one and this one are in parallel. See this one? This effective is half, this one is a half, so half of. This two are in series, so they become 1 ohm. 1 ohm and 1 ohm are in parallel, so effective is half. This is 2 by 3, this one is 2 by 3, so 2 by 3, 1 by 2, 2 by 3. They are all in series, so R is equals 11 by 6. So 11 by 6 ohm. This symmetrical circuit will also get the same value, 11 by 6 ohm. And then if you look at the case, this is a potential point. So this is 1 ohm and 1 ohm. As they are in series, the effective resistance is 2 ohm. So all these three are in parallel. So the effective value of resistance comes as 22 divided by 35 ohm. Question number 12. A prism is made up of a wire mesh with each side having equal resistance R. A battery of 6 volt and 0 internal resistance is connected across E and F. E and F. As shown. The current in the branch AD. If R is equal to 5 ohms, all the resistances are 5 ohm, they are connected in the form of a mesh to form a prism, right? Now they are asking you to calculate what is the current through this path AD. So we can reconstruct the diagram here. Question number 12. We can reconstruct the diagram in this form. This is how the circuit is reconstructed. This is a 6 volt potential. All the resistances are same, 5 ohm each. They are all R. They are all 5 ohm each. R equals 5 ohm. Potential equals 6 volt. They are asking you to calculate what is the current through this path AD. So this is BC and this one is AD. What is the current through this path AD? Current through the path AD. Idea is very simple. If you look at this particular case, from E, A and B are at the common same potential, D and C are at the same potential. Similarly, from F, A and B are at same potential, D and C are at same potential. As we saw, when you go from E, you check out how many resistors are falling between the 2 points. From A to R, between E and F, we have to check out. E and F, I can take A, B, C, D. A, B, C, D. From E to A, 1 resistance. From E to B, 1 resistance. From E to C, 2 resistance. From E to D, 2 resistance. The same way, from F to A, 2 resistance. From F to B, 2 resistance. From F to D, 1 resistance, F to D, 1 resistance. If you look at the case, A, B are at same potential, C and D are at same potential. So this path can be excluded. This resistance, this is redundant. In the sense, this is excess. So this resistance can be taken out. Now, E, A, D, F, this is in series. E, B, C, F, this is in series. And these two are in parallel with this R and with the potential 6 volt. So I have a potential of 6 volt across this path. What is common in parallel combination? Potential is common. So potential is common in all the 3 paths. So potential is 6 volt here across E and F in this particular point. So I can calculate current through the path AD. If I1 be the current entering through the path and I2 be the current flowing through this path, let us say this current is divided as this one. Let us say this one is, I can mark this one as I1 and this current as I2 and this one become I3 and I4. It gets divided up as I3 and I4. What I want to calculate is I4. The same current I4 will be flowing through this path because this is in a series combination. So all the 3 resistances are in series. Effective resistance is NR, identical resistance. So NR, series resistance will give an effective resistance value NR. So total resistance is known, total potential is known. We can easily calculate current. I equals V divided by RS. Potential is 6 volt. RS is NR. Number of resistance is 3. Value of resistance is 5. So 6 divided by 15. I can write it as 12 divided by 30. 0.4 ampere. Current through this path is 0.4 ampere. So this is the one. C option. Thing is that if a meshy circuit is given, first you should know how to reconstruct the circuit. Actually, these points are common potentials, right? These points are at common potentials. So from this point, we have to extend the circuit. We will be getting a circuit like that. And then we have to apply the rule what we discussed earlier. Right. Question number 13. In the arrangement shown, the magnitude of each resistance is 2 ohm. All the resistances are 2 ohm. The equivalent resistance between the points O and A. They are asking you to calculate the resistance between the points O and A. Once again, this circuit also has to be reconstructed. Now, question number 13. In the given circuit, they are asking you to calculate the effective resistance between OA. All the resistances are R. This is BCD. As the circuit is symmetrical about this particular line OA, we can say B and D are at same potentials. B and D are at same potentials. So we can reconstruct the diagram in this form. Just look at the diagram. I am taking this as the reference line. This point is C, this point is O, and this point is A. And now I am connecting these 2 points which are at common potential. B and D are connected. So I will get 2 resistance. This is B comma D. Like this. And these 2 resistance will come in parallel and they are connected to BD. In the same way, these two resistors will come parallel and they are connected to BD. Now, all the resistances are R ohm. And the resistance value is given 2 ohm. R is equal to 2 ohm. Now, these two are in parallel. Effective resistance. Rp equals R square divided by 2R. So R by 2. R by 2. As R is 2 ohm, 2 by 2 is 1 ohm. So this value will become 1 ohm, this value will become 1 ohm, and this value will become 1 ohm. The circuit can be reconstructed like this. B, D is the point from where I have 1 ohm resistance, then 2 ohm resistance, then this is 1 ohm resistance, this is 2 ohm, and this one is 1 ohm. This is how the circuit is reduced. Now, what is required is the effective resistance between O and A. If you look at the diagram, these two are in series, 2 and 1 are in series, and the effective resistance is parallel to this 1 ohm. So I can once again reconstruct this as 3 ohm because these two are in series. So R is equals 2 plus 1, 3 ohm. So I have 3 ohm resistance here, 1 ohm resistance, and then this 2 ohm is still there, and this is 1 ohm. This is 1 ohm resistance. 3 ohm and 1 ohm are in parallel. We have to calculate the effective value. Rp equals 3 into 1 by 3 plus 1. So 3 divided by 4. The effective value of this resistance becomes 3 by 4. Between OA is asked. 3 by 4 and 1 are in series and 2 is in parallel. 3 by 4 and 1 are in series, so R is equal to 3 by 4 plus 1. So it is 7 divided by 4, and 7 by 4 ohm and 2 ohm are in parallel. So I can write Rp equals 7 by 4 into 2 divided by 7 by 4 plus 2. So 14 by 4 divided by 15 divided by 4. Can cancel this. I will get 14 divided by 15. So effective resistance between O and A is 14 divided by 15 ohm. This is the route by which we are simplifying the circuit. The final step, we are getting the effective resistance value as 14 by 15. Question number 14. The equivalent resistance between the points A and B. The circuit is as shown. They are asked to find out the effective resistance between A and B. We can reconstruct the circuit here. Question number 14. The resistors are connected like this. From this point there are 3 resistors. And they are connected like this. This is the point A, and this one is B, and this point is C. All the resistances are given the value R. If this point is A, then this point also has the same potential, this one also has the same potential. Up to this point they are at the same potential. So I can connect all the same potential points so that 1, 2, 3, 4, all the resistances will come parallel from C to A. 2, 3 and 4. All the 4 resistance will come parallel. And this resistance R and this resistance R are separate. These 4 resistors are connected parallel because these are all common potential points. Now, if resistances are all identical and if they are all connected in parallel, Rp is equal to R divided by N. Since there are 4 resistances, I can take R by 4. So that this circuit reduces to R by 4 ohm resistance, R ohm resistance and R ohm resistance, B and A. If you look at the case here, B, C, A, this path is straight, so these two are said to be in series. So in the series combination, R is equals R by 4 plus R, 5 by 4 R. This is the effective resistance for these two resistors because these two are in series. Now this circuit reduces to AB and then 5 by 4R. These two resistances are in parallel. Now we need to calculate the effective value of the resistance here. Since they are in parallel, RP is equal to 5 by 4R into R divided by 5 by 4R plus R. 5 by 4 R square divided by 9 R divided by 4. 4 gets cancels out, R gets cancels out. We will get 5R divided by 9. So the effective resistance between A and B is 5 by 9. 5R divided by 9. So first option. Now, question number 15. The equivalent resistance between the points A and B of the network is shown here. The equivalent resistance between the points A and B of the network is. Now, we can draw the diagram here and then we can reconstruct. Idea is very simple. Question number 15. The circuit diagram is as shown. This is A. And we have another resistance. This is point B. And one more resistance is there. As we look at the circuit diagram, it seems to be very complex, but idea is very simple. The resistances are 2 ohm, 3 ohm, 2 ohm, and this one is 4 ohm, 2 ohm, 1 ohm, this one is 10 ohm, and this one is 1 ohm, 1.8 ohm, 2.2 ohm, and this one is 5 ohm. They are asking you to calculate the effective resistance between A and B. As you look at the circuit, it seems to be very meshy, but idea is very simple. Thing is that these ends are open, so these paths are redundant, which means these resistances are excess. No current will flow through these paths. So this one is also redundant, excess of resistance. No current will flow through this path. So I can delete this 10 ohm resistance. I can take out this 1 ohm resistance, and I can take out this 2 ohm resistance. Now, if you look at this particular connection, it starts from this point and connected to the same point. Actually, if you connect these two, these two are at the same potential. If you connect these 2 points, this circuit is said to be short circuited. This path is short circuited. So, what will happen? This circuit will also go off. This path will also go off. That's all. This is the remaining part of the circuit. This is a short circuited circuit. Actually, these 2 points are connected. The ends of the wires are connected to the same point. So, it has no role at all. If I am having a circuit like this, what will happen? The current will flow and then once again it will meet at the same point. So it is of no use. This is simply a knot. This is a short circuit. There is no need of it. So I am just removing that also. This is the remaining circuit. So there is an excess wire. So I can take this 4 ohm resistance to this point. So this 4 ohm, this 2 ohm and this 3 ohm and 1 ohm are in parallel and their effective is in series with 2 ohm and 5 ohm. So I can reconstruct the circuit as 2 ohm and then 3 ohm, 1 ohm, 2 ohm and 4 ohm, and this is 5 ohm, this is B. This is 5 ohm 3 ohm, 1 ohm, 2 ohm and 4 ohm. 3 ohm and 1 ohm are in series and their effective is 4 ohm now. 4 ohm, 2 ohm and 4 ohm are in parallel. So 1 by Rp equals 1 by 4 plus 1 by 2 plus 1 by 4. As you know, 1 by Rp equals 1 by R1 plus 1 by R2 plus 1 by R3. So 4 is taken as LCM 1 plus 2 plus 1. So 4 by 4, 1 ohm. The effective resistance of all the 3 resistors is equal to 1 ohm. 2 ohm, 1 ohm and 5 ohm are all in series. So what is the effective value? All the series resistors are added up simply. 2 plus 1 plus 5, this is 8 ohm. So the effective resistance between A and B is 8 ohm. B option. So how to simplify the circuit? This one is redundant, so no current flows. This one is redundant, no current flows. This one is redundant, no current flows. This one is short circuited, so this is removed. So the remaining circuit is this one, this resistor, this resistor. These are all in parallel and the effective is in series. Simple. Number 16. In the circuit element given here, if the potential at the point B is VB equals 0, then the potentials of A and D are given as. What is the potential of A and what is the potential of D? Just look at the diagram. 1 ampere current is flowing. This is potential point A and this one is B. This point is C and this point is D. They are asking you to calculate the potential at A and the potential at D, and they have given potential at B is 0. Current flow is said to be 1 ampere and the resistance values are 1.5 ohm, 2.5 ohm and potential is 2 volt. Fine. 2 volt. Now, by applying Kirchhoff's law, as we know very well, if we move from low potential to high potential, minus 2 plus, then this one will be taken plus V. This is direction of travel. As we move from high potential to low potential, this is the direction of travel, this is minus E. If we go along the direction of flow of current, if the direction of travel is along the direction of flow of current, then we can take this as minus of I into R. If the direction of current is in one direction and the direction of travel is in the opposite direction, then this must be taken as plus IR. Now you apply this sign conventions to this particular circuit. Idea is simple. VA is the potential point. As I am going along this direction, it is the product of current and the resistance. So 1 into 1.5, it is 1.5 volt. I am using minus sign because I am moving along the direction of travel is along the direction of current. So it is minus 1.5 volt and this is equal to VB. I am taking this point as reference point because VB is given 0. If VB is 0, then VA minus of 1.5 is 0. VA equals 1.5 volt, that is positive. Now, you need to calculate the value of potential at D. I am starting from this point, VB. And the same current is flowing along this path because this is a straight path. Same current, 1 ampere, 2.5 ohm resistance is there. Product of current and the resistance will give you potential. So, minus of 2.5 volt. Actually, I am traveling along the same direction of current, so I am using minus sign here. And then I am going from low potential to high potential. So as the direction of travel is from low potential to high potential, then it is positive. So plus 2, then that will be equal to the potential at a point D. So VB is 0, minus of 2.5 plus 2 is minus 0.5. This is equal to VD. So potential at a point D is minus of 0.5 volt. So VA is plus 1.5 volt and VD is minus of 0.5 volt. Option is D. Now, question number 17. Find the value of resistance R for which no current will flow through the 5 volt battery. No current will flow through the 5 volt battery. What is the value of the resistance R? This is what is asked. Now, Question number 17. This one is question number 16. Circuit is given. A, B, C, D, E, F. This is 1 ohm, 5 volt, 10 volt, 1 ohm, and this is R. They are asking you to calculate what is the value of R. If you look at this condition given, there is no current flowing through the 5 volt battery. So through this path, there is no current. If there is no current, then we can say the potential is exactly 5 volt across E and F. Potential is 5 volt across E and F. If any current flows through this path, then the potential will be less than the EMF. No current is flowing, so potential and EMF are equal. If this potential is 5 volt, then potential across this path is also 5 volt and across this path is also 5 volt. Now, this path is not there because no current is flowing. This is neglected. Only idea from this circuit is that we are getting the potential across E and F. The same potential will be existing across C and D. If this is 5 volt, this is also 5 volt. Now, I can write the expression for current as I equals V divided by R in this closed path. So, total potential is 10 volt. Total resistance is R plus 1. This is I equals 10 divided by R plus 1. This is the expression for current. I can write this as IR plus I equals 10. Also, if you look at this expression, IR is equal to 5 volt. Actually, IB the current flowing through this path. I into R. Potential difference is already given as 5 volt. So IR is 5 volt. From the diagram, we are getting the data. If this is 5 volt, this is also 5 volt. IR is equal to 5 volt. If I substitute for IR equals 5 volt, it is 10 minus of 5. This is 5 ampere. I equals 5 ampere. What is asked is the value of resistance. Resistance R is equal to V divided by I. R equals V divided by I. What is the potential difference across this path? 5 volt. Current through the path 5 ampere. So this is 1 ohm. This resistance value R is equal to 1 ohm. Resistance value R is equal to 1 ohm. So what exactly we are doing is, we are considering the data given. Through this path there is no current flowing, which means the potential difference between this path E and F is 5 volt. If this is 5 volt, a parallel connection also has a potential 5 volt. Right? Then from this idea, I am taking IR, the product of current and resistance, as 5 volt. This is the data I am obtaining here. And then in the closed path, I can take the value of current as I equals V by R. Potential is 10 volt. Total resistance in the circuit is R plus 1. So IR plus I equals 10. As IR is 5, I will be 5 ampere. Resistance is V by I. 5 by 5 is 1 ohm. Now, question number 18. In the circuit shown in the figure, the potential difference between points A and B is 16 volt. Potential difference between A and B is 16 volt. Find the current passing through 2 ohm resistance. They are asking you to calculate the current flowing through 2 ohm resistance. You have to apply Kirchhoff's law here. Kirchhoff's voltage law. Question number 18. A resistor, a battery, and another resistor, cell, and B. This is A, 4 ohm, 9 volt, 1 ohm, 3 volt, 4 ohm, and they are asking you to find out the current flowing through this 2 ohm resistor. Now, before starting this question, I can consider the current flowing through this path is I. As it approaches the junction, current will divide out as I1 and I2. As it comes here, I1 and I2 together, combine together and flows as I. Now, you have to apply Kirchhoff's law here, Kirchhoff's voltage law here. The algebraic sum of the products of currents and resistances in each part of a closed circuit is 0, or is equal to the algebraic sum of the EMFs in the closed circuit, net EMF round the closed loop, or net potential round the closed loop is equal to 0. I can say here if current is I can write the potential difference across VA and VB is given 16 volt. It is mentioned 16 volt. So I am starting from this point in A, VA. I am taking the travel along the direction of flow of current. So product of current and resistance is taken minus. So 4I. High potential to low potential, so negative, minus 9. Then once again, current into resistance is minus 1. Low potential to high potential, so positive 3. Then once again, along the direction of flow of current, I am taking the product of current and resistance, so 4 into I. This is equal to VB. This is important. This is how the circuit must, or expression must be brought out. So VA minus of 4I. What is the meaning for this? If I start from VA, there is an amount of potential. The potential is dropped across each and every resistance as I go along the path of the resistor, and the remaining potential will exist at B. So from total potential, these potentials are dropped, and finally I am getting the potential VB. This is the meaning. So VA minus of VB is equal to minus of 4 minus of 4I plus 8I, minus 9 plus 3 minus 6, as it goes that side, plus 6. I'm sorry, here the current is I1. From this path, the current is small I1. So this one is product of current into resistance is I1, small I1. So minus I1 goes that side, so it will become plus I1. This is plus 8I. So minus 4I plus 8I, minus 9 plus 3 minus 6, as it goes that side, plus 6, minus I1 becomes plus I1, VB can this side, so VA minus VB. So 16 equals 8I plus I1 plus 6. As I take this 6 here, I will get 10. 10 equals 8I plus I1. So 8I plus I1 is equal to 10. I have taken one expression. Now, I am taking this closed path alone. This closed path alone. I am starting from this particular point. So, high potential to low potential, minus 9. Then, current into resistance. When taken as a product, I will get I1 minus I1. And as I move along this direction of travel is opposite to the direction of current. So, positive plus 2I2. This is equal to 0. The total potential is equal to 0. Actually, what is I2? If I is divided out as I1 and I2 is I minus of I1. So, minus 9 minus I1 plus 2 into I minus of I1, this is equal to 0. Minus 9 minus I1 plus 2I minus 2I1, this is equal to 0. So, we can write minus 9 minus of 3I1 plus 2I minus 3I1 plus 2I equals 9. This is the second equation. Solve this equation and get the result. You have to find out the value of I2. So we need to know the value of I1 as well as I. So I am taking this expression 8I plus I1 equals 10. Then 2I minus of 3I1 is equal to 9. I am multiplying this expression by 2 and this expression by 8, so that this will become 2 into 8, 16I, 2 into I1 equals 20. Then when this is multiplied, this is 16I minus 24I1 equals 72. So if you take a difference, this will cancel out. Minus of minus is plus. So 26I1, this is equal to minus 52. What is I1 then? Minus of 52 divided by 26, minus 2 ampere. So I1 is minus 2 ampere. I1 is minus 2 ampere. substitute I1 in any one of the equation and get the value of capital I. So I can take 8I plus of I1, which is minus 2, this is equal to 10. 8I is equal to 10 plus 2, this is 12. I equals 12 divided by 8, 3 divided by 2, 1.5 ampere. I2 equals I minus of I1, so 1.5 minus of minus 2, so 3.5 ampere. So current through this path is 3.5 ampere.